It's 9:30, so let's go ahead and get started. Welcome to the predictive control session this morning. This is a rapid interactive session, and so there'll be two parts to the session. First, we'll have the video presentations until 11 o'clock, and you'll just stay in this Zoom room for that. And then it will be followed by the interactive portion of the session from 11 to 11:45. In that case, each presenter in the session, the 22 presenters, have their own Zoom rooms, and you can go back to the main schedule, find 11 o'clock sessions, and you can find the links to their Zoom rooms. But until 11 o'clock Mountain Daylight Time will be, you stay here in this Zoom room. And also, I want to note that we're going to have a People's Choice contest and award. And so I put the link for that in the chat. You need to enter your favorite talk by noon today. And then also consider nominating papers for the Hugo Schuck Award. That link is also in the chat. So in the rapid interactive session, we have the 3-minute talks. But we're gonna kick off the session with a keynote presentation, which is a 15-minute presentation. And please do ask questions in the Q&A feature at the bottom of your screen. And Helen Durand will be able to answer questions during and after her presentation. With those instructions, I'd like to go ahead and introduce our keynote speaker this morning, Professor Helen Durand from Wayne State University. And she's going to be presenting the work of Helen Durand and Matthew Wagner, mitigating cyber attack impacts using Lyapunov-based economic model predictive control. Thank you, Helen.
This talk is titled Mitigating Cyber Attack Impacts Using Lyapunov-based Economic Model Predictive Control, and it will discuss work performed by Helen Durand and Heikki Oyama and Matthew Wagner at Wayne State University. The focus of this talk is on cybersecurity of control systems, which is needed for maintaining expected operation of critical industrial components and infrastructures. Attacks on industrial control systems can seek to impact, for example, profitability of operation or process operational safety by manipulating the actuator behavior. Information technology solutions provide one means for seeking to address cybersecurity concerns for control systems. Other engineering strategies can also be explored, such as techniques for attack detection from data, inherently safe process designs to prevent attacks on the control system from causing safety problems even if they occur, or control designs that perhaps combine with a detection method to enable safe operation. This talk focuses on the latter type of cyber attack resilient control strategies, or those which combine with detection algorithms. The concern for controllers which gain a level of resilience from a detection mechanism is that an attacker can evade that mechanism or be stealthy. Control theory can help with developing detection methods that take advantage of controller guarantees in the sense that when there is no detection of an attack, closed-loop stability is guaranteed for at least some subsequent amount of time via the co-design of the controller and the detection mechanism. This talk focuses on co-design of control and attack detection methods for cyber attacks on nonlinear systems, with a focus on a specific control formulation known as Lyapunov-based Economic Model Predictive Control, or LAMPC. We focus on this control design due to its strong theoretical properties even in the presence of sensor noise and plant model mismatch. We primarily focus in this talk on a state feedback LAMPC with an attack detection strategy based on comparing state predictions and measurements at each sampling time. We close by mentioning that an LAMPC that receives state estimates instead of state measurements for a process equipped with multiple and redundant state estimators may provide another concept for co-design of control laws and detection algorithms with guarantees. In general, cyber attacks can be performed to break a typical control loop at some point. In this talk, we focus on cyber attacks that break the control loop between the sensor and the controller and provide false sensor measurements to the controller. This prevents true process knowledge from being obtained by the controller. As we will see later in this talk, this cannot be handled by techniques for handling sensor measurement noise alone. In our development of cyber attack detection and control techniques, we will focus on the class of nonlinear systems shown here. This is a class of input affine nonlinear systems with state X, input U, and disturbance W, all of which are bounded. We consider that the origin is a steady state for this system and that the system is stabilizable in the sense that there exists an explicit stabilizing control law h of x that can render the origin asymptotically stable in the sense that there exists a Lyapunov function v with a negative definite time derivative along the closed loop state trajectories without disturbances for all states in a neighborhood D of the origin. We define a level set of the Lyapunov function contained within the region where v dot is negative as the stability region, shown in the figure on the right. We consider that full state measurements are available continuously for this system, but that they are impacted by bounded measurement noise. For this class of systems, we will be exploring the impacts of cyber attacks on sensors for the feedback control law known as economic model predictive control. The general formulation of an economic model predictive controller receiving feedback of the full state is shown on this slide. It consists of a general stage cost, dynamic process model, state measurement, input rate of change constraints, and input and state constraints. The input rate of change constraints may be added to prevent the control actions computed by the EMPC from being overly aggressive. With additional constraints to be discussed subsequently, this control formulation has theoretical guarantees regarding feasibility and stability in the presence of sufficiently small bounded measurement noise and disturbances. False sensor measurements do not ensure boundedness of the error in the state measurements, and therefore do not necessarily allow these guarantees to be maintained. The additional constraints which allow the closed-loop stability guarantees just described to be obtained are Lyapunov-based stability constraints that, when added to the EMPC formulation on the prior slide and with a slight change in the way the input rate of change constraints are enforced for feasibility reasons, give a formulation of Lyapunov-based EMPC or LEMPC. This control formulation has two modes of operation, where the first utilizes the constraint shown in red. This constraint requires the state predictions to remain within a subset omega rho E1 of the stability region omega rho. This constraint is designed using the explicit stabilizing controller h of x, and that controller is guaranteed to meet all state and input constraints at every sampling time. This control law also allows us to guarantee that the closed-loop state is always maintained in the stability region omega rho, and also to ensure that the measurement, even though impacted by noise, is also maintained in omega rho. The second mode of operation of LEMPC allows both feasibility to be guaranteed as well as stability, in the sense that if the mode 2 constraint, shown here in blue, which enforces a decrease condition on the Lyapunov function, is enforced repeatedly, it can drive the closed-loop state to a neighborhood of the steady state. Though the control law just described has attractive stability properties, cyber attacks on state measurements provided to that controller could prevent those stability guarantees from being realized. This is because even though the guarantees just described can hold in the presence of sufficiently small sensor noise, a cyber attack may act like insufficiently small sensor noise. This indicates that it would be desirable to detect an attack by looking at the deviation of measurements from the actual state. A method of approximating the actual state is through state predictions from the last measurement. This gives one idea for a cyber attack detection strategy for LEMPC. The difference between the measurement and the prediction of the state could be checked at each sampling time. If the difference is larger than an expected threshold, the state measurement can be flagged as a possible attack. If it is below a threshold, it should be able to be tolerated by the controller for the subsequent sampling period in the sense that the closed-loop state should still be within a bounded region of operation at the end of the sampling period. Based on the fact that LEMPC with sufficiently small measurement noise can retain closed-loop stability in this sense, it should be possible to design an LEMPC that can maintain the closed-loop state in a bounded operating region after what I'll term a sufficiently small cyber attack, meaning one which does not trip the detection mechanism, occurs. In this discussion, we see the concept of controller and detection mechanism co-designed for LEMPC, in that the resilience of the controller to the cyber attacks that are not detected for at least a sampling period after the attack occurs will come from the LEMPC's design in tandem with the threshold design on the attack detection method. Here, we note benefits and limitations of the proposed method. Some of the benefits are that it offers a way of flagging attacks based on state predictions, and it allows closed-loop stability to be guaranteed for a sampling period after an attack that does not cause too large of a deviation of the falsified state from its predicted value. Because closed-loop stability is guaranteed for the subsequent sampling period, this gives some buffer time for a potentially secondary detection mechanism to attempt to detect the attack after its occurrence before the closed-loop state leaves a safe operating region. If the attack is detected by such an auxiliary detection mechanism, backup strategies can be activated to maintain safety at all times. A significant limitation of the method, however, is that it does not guarantee closed-loop stability after a single sampling period following an attack. This is because it relies on a state prediction from the value provided as the sensor measurement at the last sampling time. Once the last sensor measurement is falsified, the predictions coming from this value are no longer representative of the process state. This can be thought of like the state never receiving true feedback when an attack is occurring, and like sensor noise having a potential ability to grow over time. We will now provide an illustrative example to clarify the concept that cyber attacks resulting in falsified state measurements, if they are close to the actual values, may not cause an economic model predictive controller to show closed-loop stability issues in a sampling period, even if Lyapunov-based stability constraints are not used. We also demonstrate potential issues with continuously falsified measurements. In this example, a continuous stirred tank reactor with a second-order exothermic A to B reaction is examined. The control objective is to optimize the economics of this CSTR while maintaining safe operation. The economics-based objective function to be maximized by the EMPC is the time integral of the production rate of the desired product. Manipulated input constraints are enforced for physical reasons. 5 cyber attacks on the sensors were performed on this system at T0 by providing combinations of CA and T with the values of CA and T in the ranges noted. These falsified state measurements resulted in the inputs shown on the right, where different colors represent different scenarios, and the black trajectories are those corresponding to the unattacked case with true sensor measurements. It can be seen from the figure that the inputs computed under the various scenarios were quite close. These led to very similar state trajectories that are overlapping on the left. This indicates the principle that in the presence of a cyber attack, for which there is a small difference between the actual and falsified state measurements, the inputs computed by an EMPC may not be significantly different. This highlights as well the reasonableness of the proposed method for cyber attack detection and closed-loop stability, involving checking how significantly a state measurement and an expected value of the state coming from the prediction differ. Next, we look at how measurement noise and false sensor measurement cyber attacks can differ. Here, we provide a false state measurement to the controller at every sampling time and look at how the actual state evolves compared to the false state trajectory. The false state trajectory is obtained by simulating the process dynamic model, where at every sampling time, the initial value of the false state measurement is set to be 0.2 kilomole per meter cubed and 5 Kelvin above the predicted values. These are being predicted from the last value provided as the measurement to the EMPC, which was false. The simulations indicate that despite that at every sampling time, the falsified state measurement is within a bounded amount of the values predicted from the prior value provided to the LEMPC, there is a potential for error between the predicted and actual state to grow over time. This demonstrates the concept that measurement noise and false sensor measurement cyber attacks are not equivalent, because while with measurement noise there is some error at every sampling time, that error is within a range of the actual measurement. In contrast, in false sensor measurement cyber attacks, effectively, feedback of the process state is not obtained, perhaps not even approximately. These simulations highlight that a key limitation of the proposed method for attack detection and resilient control is that the detection technique relies on state predictions. Once one measurement is falsified, the predictions are no longer reliable. A concept for overcoming this is to replace the state feedback LEMPC with an output feedback LEMPC, meaning an LEMPC that utilizes an estimate from a state estimator in its design. If redundant state estimators are available and only the one used to provide estimates to the LEMPC is impacted by a sensor measurement attack, the others can be utilized to flag this because, in effect, they provide a check on whether the state estimate being received by the LEMPC is sufficiently accurate. In conclusion, detection mechanisms using LEMPC may take advantage of control theoretic guarantees in detecting attacks. In this work, we focused on a state feedback LEMPC formulation that was considered to mitigate cyber attacks in the sense that it guarantees closed-loop stability over a sampling period in the presence of disturbances, measurement noise, and false sensor measurements within a bound on the error between the prediction of the state from the last measurement provided to the LEMPC and the state measurement at a given time. When the attack is not sufficiently large to be detected at a sampling time, then if an auxiliary detection mechanism does not detect it during the subsequent sampling period, closed-loop stability could be compromised after that time. To overcome this, other techniques could be tried, such as using an output feedback LEMPC with multiple redundant state estimators, where only the estimator providing estimates to the LEMPC is assumed to be able to be impacted by false sensor measurements. We gratefully acknowledge financial support from the National Science Foundation and Wayne State University.
Hello, everyone. My name is Caden Plew, and I'll be presenting this work today that's titled A Supervised.
Thank you so much, Helen.
Thank you.
Wonderful. Okay, so we can take questions now, and you can type them into the Q&A. So you're not able to speak up here, but you can share your questions in the Q&A. And Helen can answer them. I'll start with one question. Thanks for a really interesting talk. If there is model error, how would you think about incorporating accuracy of the model?
We do incorporate that in the strategy that we have. So the strategy can handle both bounded disturbances, which can include the plant model mismatch, as well as bounded measurement noise.
I guess I'm just thinking, if you're getting error in the measurement, or that difference, it could be an attack, or it could be that the discrepancy is due to model errors. But I guess you like you say, you need to put bounds on modeling error, and it just seems like that could be tricky in practice.
Yeah, with regard to, from a theoretical perspective, you can make predictions of like how far is the maximum amount that the state prediction should differ from the actual if your last state measurement was not false. And then you could say, and here's also my detection threshold. And then you can design your stability region for your controller sufficiently conservative to handle sort of the combined error coming from how far off you believe a good prediction could be, plus the amount of threshold that you're going to use for detection.
Okay, so we have a couple of questions here in the box. First one, how did you choose the magnitudes, trajectories of the false measurements?
Yeah, that's a great question. So for this, we were doing a theoretical characterization of how would you be able to guarantee closed loop stability and what are different strategies. And so it does require, for the first detection strategy that relies on the state predictions, that does require that the measurement or the falsified values, in order for you can set a threshold on how big those can be. And then you can use that in designing your stability region. So the bigger that you allow this threshold, then the more conservative you have to make your stability region. So then that can help you detect them. And if they're lower than that bound, then you use that to say anything lower than that bound, I use that to design the stability region, and then I guarantee stability for one subsequent sampling period.
Okay, let's move on to next question. We've got a bunch of questions here. So next question, could this methodology be combined with detection methods that detect drifts like EWMA? Do you envision this implemented in each unit operation in a plant separately? Given that it solves an NLP, how would it scale for plant-wide cyber attack mitigation? So maybe there are 3 questions there, but you can answer some or all of those.
Yeah, sure. So for the first one, so certainly you could add multiple detection mechanisms all at once where you're using multiple to try to sort of like redundancy and maybe multiple layers of protection, that being the idea. In terms of though those detection mechanisms, so I guess let me clarify. So we have two detection mechanisms in this, one of them with state estimates and one of them with state predictions. If you use the one with state predictions, that can only guarantee you have stability after one sampling period after an attack occurs, or else the state predictions are messed up. So then you would at that point need some, in order to be able to detect it after that, you would potentially need some type of additional auxiliary detection mechanism in order to get it after that point. So then you could try to combine with those. Then whether other attack detection mechanisms would have guarantees is a different story. The one with the state estimates, you can make guarantees that you detect things based on the properties of the state estimators having meeting certain assumptions with regard to them converging to a neighborhood, the estimates converging to a neighborhood of the actual states. Then you do have to require that not all of the estimates are being impacted by the attack in order to make the guarantees. In terms of envisioning this implemented in each unit operation in a plant, that's a good question. This looks at a centralized EMPC design. I have not looked at something that might be distributed to try to go in different units one by one. For solving an NLP, so this is also a good question. In terms of the way that this works, is a centralized EMPC design. So I think that the cyber attack issue with that is not really different than normal EMPC. That doesn't really add additional computation time except for maybe calculating the state prediction. So I would say it probably scales about as well as normal economic model predictive control designs would. Then the next question is, how do you get the state predictions? So for that, we assume that we have a first principles dynamic model. As Martha asked, then of course there could be some modeling error between the first principles and the actual process dynamics. But then that is where the bound comes in, and that you can say, okay, if I have a actual process model and I have a potentially somewhat not fully accurate process model, you can make a bound on how far off your predicted value would be from the actual state if the value of the measurement that you got at the last time had bounded measurement noise. So you can make a bound on how far off your state and your prediction would be, even with the measurement noise and the disturbances. And then that's the state prediction that we would be using. How do the redundant observers not feeding into the controller be unaffected by cyber attacks? So basically that's a very good question. So that would be, those observers would have to not be receiving the same, the measurements that are being falsified. So the idea would be only a subset of your controllers for that, or a subset of your sensors for that one would be able to actually be attacked. Not all of them could be. And that would be the way that you would get some of the estimators that are receiving output measurements that are not having a problem.
Great. Well, great set of questions. I maybe just have one last brief one, which is there any historical evidence of anyone in a chemical plant or generally doing cyber attack? Do you have examples, or, I mean, either way, it's important to plan, but I'm just curious if there have been cyber attacks.
Yeah, that's also a really good question. So I will give a twofold answer. So one is, there are examples of cyber attacks getting into industrial systems. And there have been an attempt for people to cyber attack a safety system somewhere in Saudi Arabia for a chemical process. But then there have also been, a very famous one is this Stuxnet one in Iran that was actually able to destroy some centrifuges at a plant. Those ones, I don't know all the details of all of them. The Iran one was had like many different levels. Like there was different things, many different things going on with it. So it's not as simple as like what we're showing here with just like, oh, you just get a false sensor measurement. So that was not what happened in the Iran case as the sole thing that was going on there. But in terms of cybersecurity is very critical. In the process industries, there is a lot of concern about it. There's not always a lot of publishing of exactly all the details, I think, because there's a lot of regulations that govern things, and then it could be sort of a little bit scary because it could verge on like whatever espionage and terrorism and all those things. So it is a problem, but exactly how they're all being carried out or what types of attacks are being carried out on chemical plants, all the details of that, I'm not sure, but I know it's an issue. Think about them in general.
Great. Great. Well, thank you so much, Helen. I think it's time for us to move on to our rapid presentations, but thank you very much for kicking off the session and for
Thank you so much.
sharing all your perspectives. Thank you. Okay, so let me just make a brief announcement. So now we're going to move on to our 21 3-minute presentations. So we're going to play them straight through for the next hour in this Zoom room. So just enjoy, and please do nominate your best one, vote in the People's Choice, which is in the chat, as well as consider papers to nominate for the Hugo Schuck Award. And then at 11 o'clock, you can move on to new Zoom rooms to visit the individual presenters and ask additional questions, sort of like a poster, and they'll have content on their screen to share, and you can go visit the, so please do, pick out the ones that are most interested to you. We're not going to have questions during this rapid period, but please save your questions, and then you can go talk to the presenters in their own individual Zoom room. So for all the presenters here, then make sure you do go to your Zoom room at 11 o'clock so people can come and visit you there. So with that, let's go ahead and start the rapid presentations.
Hello, everyone. My name is Caden Plew, and I'll be presenting this work today that's titled A Supervisory Model Predictive Control Framework for Dual Temperature Set Point Optimization, which was done in collaboration with Dr. Amanda Smith and Dr. Mingji Liu. I'll start by going over the objectives that we prioritize in the design of this predictive control framework that's being used to optimize the dual temperature set point schedule in a small office building, which is selected here as the test case. Priority number 1 is occupant thermal comfort, which requires being cognizant of the occupational schedule in order to ensure that whenever there's somebody in the building trying to perform a task, that they are comfortable enough to do so. Now, priority number 2, which is coupled to the first and typically inversely proportional to it, is the cost of HVAC operation, which in our case translates to HVAC power demand and also HVAC energy usage. Now, the main contribution of this work is the fusion of emerging technologies in both building modeling and building optimization, with the purpose of developing a supervisory predictive control framework that can be extrapolated into the real-world complex building domain. Now, here we start by deriving a data-driven building model with the intention of limiting the number of inputs to be as small as possible. And here we were able to get that down to just 7 inputs. And each of these 7 inputs are typically readily accessible to the building manager. Now, with this building model, it can be used in a multi-objective optimization problem over the prediction horizon in order to, again, focus on minimizing the power demand and energy usage while maintaining thermal comfort and operating within our given constraints. From this, we get the optimal temperature set point schedules that we can then apply to the real building, or in this case, a detailed building model that we're using for testing. These are the main results that are presented in the paper, where we show an average 35% energy reduction across 3 different simulations with minor gains and reductions in thermal comfort. Now, in the plot here, in the first row, we're showing the HVAC power demand across 3 different simulations, one in February, July, and October, so 3 different seasons, all in Salt Lake City, Utah. In the second row, we show the corresponding temperature set point schedules that were selected by the predictive control framework, and we show those in comparison to the baseline, which is a static temperature set point schedule. Now here we can see how the predictive nature of this framework is modifying the operational scheduling of the building in order to meet our objectives. For example, at hour 50 in the February simulations, the HVAC system is turned on where it would otherwise be dormant. And this is done in order to reduce the energy consumption over the prediction horizon. And it is this actuation exactly that allows us to improve the energy performance of the building. That's where I'm going to stop. I look forward to further discussion in the follow-up session.
Good morning. My name is Shuwen Lu, a PhD student at Cornell University. This is the work I did with my advisor, Professor Fengqi Yu. We developed a closed-loop model predict. Good morning. My name is Shuwen Lu, a PhD student at Cornell University. This is the work I did with my advisor, Professor Yu. We developed a closed-loop model predictive control framework based on distributionally robust optimization. The ThA01 modeling could leverage the partially known distribution information and has a strong ability to efficiently hedge against the uncertainty. Therefore, we have been thinking about integrating ThA01 into MPC structure to help deal with the disturbance. However, there always exists tractability issue for ThA01 problems that some reformulations are needed to make the problems tractable. To the best of our knowledge, none of the existing literature have investigated the following ambiguity set on control problems. To fill this knowledge gap, we developed the ThA01-based closed-loop MPC framework associated with the lifted ambiguity set, which is equivalently transformed from the original ambiguity set by a lifting operator. The reason why we are interested in this type of sets is if associated with this set, the ThA01 problems can be reformulated into a traditional robust optimization problem with respect to the lifted support set. Existing literature have shown that the ambiguity sets are equivalent in describing the distribution information after lifting. Besides, when using the linear decision rule to parameterize the decision variables, the problems is eventually relaxed with improved solution qualities in terms of feasibility and optimality. We want the lifted support set to be a polyhedron such that the reformulated RO problem can be recast into an efficient linear program. In order to do that, the support set is chosen as a simple box set, and the affine function G is constructed based on principal component analysis. In this way, the lifted support set is polyhedral, and only the first-order distribution information is needed. This work is implemented on an illustrative example of motion control, a two-mass spring system as given in this figure. For comparison, the deterministic MPC, referred to as certainty equivalent MPC here, and scenario-based stochastic MPC are also implemented. The control performance is measured by the average cost to go. We can see that the proposed framework outperforms the other two methods in regulating the trajectory and minimizing the offsets from the origin. Thank you for listening.
Welcome to this talk, which is on scheduling and control over networks using MPC with time-varying terminal ingredients. I am Stefan Wildhagen, and this is joint work with my PhD advisor Frank Allgöber. We are both from the University of Stuttgart. In network control systems, a number of control loops are closed over the same shared network. A known method from the literature on shared communication systems to shape the traffic of transmitting agents and thereby prevent congestion of the network is the token bucket specification. It prescribes an average transmission period of m, but nonetheless allows for scheduling of transmissions. However, it was rarely used in the context of network control systems so far. In this work, we combine network control systems with the token bucket by considering a controller that guarantees stability of the control system and at the same time fulfillment of the token bucket specification. In particular, we consider an MPC for a joint control and scheduling of transmissions. An existing control scheme for this task is a multi-step MPC, which optimizes the transmission schedule and corresponding control inputs over a prediction horizon of P. Then it applies the first m steps in closed loop during the sampling period, which is exactly the same as the token bucket period. And then the process is repeated. The multi-step formulation is required since in general, one can only find an m-step control invariant terminal set, as the token bucket allows the transmission of an updated input only every m steps on average. However, a problem is that the complexity of the optimization problem grows exponentially with the prediction horizon, since the transmission decision at each time step can either be yes or no. Naturally, the prediction horizon must be at least m steps long, and as a result, if the token bucket period m is large, real-time capability of the control scheme is quickly jeopardized. What we would desire instead is an MPC with a sampling period of 1 as usual, since then the prediction horizon and hence the complexity could be chosen independently of the token bucket period. To this end, we consider instead m different periodically invariant sets, which are then used in this approach as periodically time-varying terminal sets. In our paper, we show that for linear systems, The search for suitable time-varying terminal costs is possible via an LMI, but the time-varying terminal sets can be constructed by adapting existing methods. Then the periodically time-varying MPC is recursively feasible and achieves convergence. In a numerical example, we consider the token bucket period of 8 and compared the times to solve the optimization problem with different prediction horizons. While for time-varying MPC, we were able to achieve quite low computation times, the computation time of the multi-step MPC is at least 0.5 seconds. For many real-time tasks, this is already too long. We conclude that a periodically time-varying MPC now allows to adjust the complexity independently of the token bucket period, which enables a trade-off between a reasonably long prediction horizon and real-time requirements, which was not possible before.
The world is becoming more digital. Everything is getting a computer processor in it from car.
Good morning, everyone. First, let me introduce myself.
The world is becoming more digital. Everything is getting a computer processor in it from cars to benches. So it is imperative that we continue to create control systems that are more conducive to digital implementation. An interesting example of this is nonlinear model predictive control, also known as NMPC. This controller has the advantages of 1, selecting the optimal control input based off the model of the system, a cost function, and some constraints. And 2, having the ability to be designed in discrete time. For output feedback, a fast discrete time observer is used because of how quickly and accurately it can estimate the states. However, an issue arises between these two. The NMPC and the observer need to be run at different sampling rates to drive the system to the origin. The controller needs a slow sample rate in order to better calculate the optimal control input, while the observer needs a fast sample rate in order to better track the states of the system. This issue is solved by using a multi-rate scheme. A multi-rate scheme is one where a downsampler is placed between the observer and the controller. This component takes a certain number of samples, then outputs the last one, which allows the NMPC to have breathing space while the NMPC takes as many samples as needed of the output to provide an accurate estimate. The importance of having the different sampling rates can be shown in the figures here. The first figure is the system when the observer and the controller are both ran at the same sampling period. The system clearly does not converge or move towards converging. The next 2 graphs show the state feedback and how performance is recovered as the observer is driven faster and faster. Again, the whole idea is to use a controller and an observer that can be designed in discrete time and ran at different sampling rates to ease implementation. Thank you for your time.
Good morning, everyone. First, let me introduce myself. I am Valentino Orsini, and I'm going to present the prepared method, 2 degrees of freedom of control and bespoke. Good morning, everyone. First, let me introduce myself. I am Valentino Orsini, and I'm going to present the prepared method, 2 degrees of freedom of control and bespoke functions as tools for a reduced complexity approach to MPC. The aim of this paper is to simplify the treatment of the major issues of MPC. These issues are the stability and feasibility problems, the complexity of the online optimization procedure. The basic point of the alternative approach proposed here is the adoption of an MPC strategy in a 2 degree of freedom of control scheme like that shown in the figure. In this scheme, the output RK of the feed-forward input estimator is used as input forcing the closed-loop system sigma F. Sigma F is given by the feedback connection of a linear time-variant plant with a linear time-variant feedback controller. Using a 2 degree of freedom of control scheme allows us to decompose the MPC problem in 2 distinct steps. The first step is the offline design of the feedback controller. The task of the controller is to guarantee the stability of sigma F as well as the fulfillment of hard constraints on some physical variables in correspondence of any admissible input RK. With the term admissible input, we mean an input whose Euclidean norm is upperly bounded by a suitably chosen scalar gamma. It is important to stress that step 1 guarantees in advance internal stability and recursive feasibility regardless of the chosen prediction horizon. The second step is the design of the feed-forward input estimator. The input estimator is an algorithm whose task is the online computation of the optimal input RK forcing the closed-loop system sigma F. This signal is computed as the solution of the constrained optimization problem shown here. To simplify the constrained optimization problem, RK is assumed to be given by a B-spline function. It is advantageous to use B-splines because they admit a parsimonious parametric representation. This allows us to drastically reduce the number of decision variables involved in the optimization problem. Moreover, B-splines are contained in the convex hull of the control points. This property allows us to transfer the northbound on RK to constraints on the relative control points. In conclusion, modeling RK as a B-spline reduces the constrained optimization problem to a much simpler least square estimation problem. Thank you for your attention.
Welcome everybody. My name is Matthias Wehr. I'm with the Institute of Automatic Control of Aachen University in Germany, and I will now talk about model predictive control of an over-actuated roll gap. Rolling is a forming process where a strip of metal is passed through two or multiple rolls with the goal to reduce the material in thickness and make the thickness as uniform as possible. Usually only a single roll is manipulated in a roll stand. Here it used to be actuated by a spindle drive which can receive a new set point only every 0.5 seconds. When the process is run quickly, rejection of occurring high-frequency disturbances is not possible. Therefore, we have integrated additional piezoelectric stack actuators in the roll stand which are capable of fast actuation. This leads to an over-actuated system with different sample times. The fact that the incoming strip thickness can be measured in advance makes model predictive control favorable. Therefore, I will propose an MPC for roll gap actuation which is able to deal with the different time scales running at a sample time of 1 millisecond for the fast actuator. The model of our system can be set up simply by two first-order systems describing the system dynamics. Both have the same influence on the roll gap S sub 0. In a standard MPC setup, the entries for both actuators in the vector of the manipulated variables alternate, as shown here. But if one of the actuators can only be set once a while, constraints during the idle times are necessary. This leaves us with many optimization variables and constraints. Therefore, we have rearranged the manipulation vector, having the entries for the spindle drive and the piezoelectric actuator one below the other. Since the spindle can only be actuated at certain times, it only needs one optimization variable for manipulation. Constraints are not necessary anymore due to reduced degree of freedoms. The control horizon of the piezoelectric actuator remains unchanged. Since the time of the spindle set point changes every iteration, the manipulated variable of the spindle moves through the control horizon of the piezoelectric actuator. Simulation results show that a full-scale MPC with constraints and the proposed MPC show nearly the same tracking performance. However, the proposed MPC needs fewer optimization variables and constraints, which is advantageous for real-time applications. Further experimental results are available in the paper proving real-time capability. I'm looking forward to further discussion with you at the upcoming interactive session. Thank you very much.
Hi, my name is Christoph Mark. I'm a PhD student at the University of Kaiserslautern in Germany, and today I'm going to present our paper about stochastic output feedback MPC for distributed systems. In this work, we extend one of our recent papers about distributed state feedback SMPC to the output feedback case. In the figure, we can see a distributed plant consisting of two subsystems. The goal is now to design distributed observers that use the local output measurements to estimate the states for each MPC controller. The overall cooperative distributed MPC is allowed to communicate over a communication network in order to solve a cooperative control task. We consider M linear time-invariant systems of the form given by equation 1. We have zero mean, independent and identically distributed process and measurement noises Wi and Di. And furthermore, the dynamics are subject to local chance constraints on the states and controls, where Xi and Ui are convex polytopes. Px and Pu are the corresponding levels of chance constraint satisfaction for the states and controls. In this work, we use the concept of probabilistic reachable sets to handle the chance constraints. The PRS are characterized through the first two moments of the error states E, where Z is the state of the nominal or disturbance-free system. The nominal dynamics are used to make the prediction within our optimization problem. The challenge hereby is to synthesize a separable error covariance matrix. In the figure we can see on the left side sigma is the true error covariance matrix, which is by definition block dense. Therefore it is not separable. Hence we have to define a block diagonal upper bound on the right side. Now each block corresponds to the ith subsystem error covariance, which allows us to use local probabilistic reachable sets based on that local covariance matrix. Then we can define a tightened constraint set Z, which is given by the Pontryagin difference between our original constraints and the local PRS. The resulting tightened DMPC problem has now the same online complexity as a nominal DMPC. The main contribution of the paper is the following. First, we present a synthesis method for distributed covariance matrices based on distributed optimization. Secondly, we prove recursive feasibility, convergence to an asymptotic cost bound, and closed-loop chance constraint satisfaction under a central convex unimodality assumption on the disturbance distributions. And thirdly, a numerical example is carried out to highlight the chance constraint satisfaction and performance compared to a central MPC. Thanks for your attention.
Hello everyone and welcome to my talk. I am Johanna Bethke from the Otto von Guericke University Magdeburg. I wrote this paper together with Xu Yu from the Jilin University in Changchun in China and my supervisor, Professor Rolf Findeisen. In this paper, we proposed a self-containing predictive control scheme for linear systems subject to additive disturbances while guarantees are given. The proposed approach is able to control real systems under disturbances, for example, to adjust wind turbines to the main wind direction or to design cruise and steering control for driving assistance systems and autonomous vehicles. Our stochastic model predictive control approach enables optimal and foresight control and is self-containing in the design, while guarantees are ensured. We considered linear time-invariant discrete time systems with chance constraints. Chance constraints allow occasional violation of the state and input constraints depending on the chosen probability P. Furthermore, we assumed knowledge of the covariance of the additive disturbance. The proposed scheme allows to choose the controller weights Q and R and the probability P of the chance constraints. Using the Riccati inequality and the controllability criterion, all control variables and sets and the control input can be directly determined. The overall control structure is shown here. The control input U is composed of the nominal optimal control input, which is the solution of the optimal control problem from the model predictive controller, and an auxiliary control input which ensures that the closed-loop real system stays close to the nominal system. The constraints of the predictive controller are shrunken due to the chance constraints in the self-containing controller design. Furthermore, our proposed approach guarantees safe operation. In particular, we have proven asymptotic stability of the nominal system, convergency of the real system to the error system, and constraint satisfaction and repeated feasibility for the given probability of the chance constraints. In addition, we have shown proof of concept simulation. In the example, a wind turbine is adjusted to the main wind direction. All guarantees are ensured while the computational burden is only as high as for conventional MPC. So let's summarize. We proposed a stochastic and self-containing predictive control scheme for linear systems under disturbances, where only the covariance of the disturbances must be known. The control scheme enables the balance between robustness and performance, while asymptotic stability, constraint satisfaction, and repeated feasibility are ensured in probability. Thank you very much for your attention. I hope I could reach your interest and would be happy to further discuss with you.
Hello everyone, my name is Magnus Kögel, and in this work we consider robust MPC with multiple tubes. So this here is basically the setup we consider in this work. We have a plant which is affected by some additive disturbance, which is unknown but bounded, with constraints on the input as well as on the state. And we want to design the controller such that it satisfies the constraints, it robustly stabilizes the closed loop system, it achieves high control performance, and it can also be implemented efficiently. And one specific candidate for such a controller is tube-based MPC, but we know that it might be constrained, and therefore we propose in this work to plan different tubes. So this is basically the setup we consider. We have here the dynamics with the additive disturbance, and the tube-based MPC, which basically solves more or less a nominal MPC problem with some additional degree of freedom. And then we have the controller, which is basically the first part of the optimal nominal input and some additional correction. And I won't go into detail, but what we see is that there are some sets as well as the gain K, which basically influence the MPC. And this gain K also basically plays a major role in determining these four sets. And then the question arises, how should we basically choose this gain K to design the MPC controller? If we take now a look at one specific example, we'll pick one gain K and then plot the sets for which the MPC is feasible. We get the set shown here in black. If we pick a different gain, we get a different set shown here in red. And then this brings us to the question, can we use both gains or both tubes? And this is then what did this work. And basically the key idea is that yes, we can do this. And we can do this by blending the tubes. And this gives then the set shown here in green, which includes both sets, the red one and the black one. And this brings us to the conclusion of this work. So we have now this MPC scheme with multiple tubes and the desired closed loop properties like constraint satisfaction and robust stability. And moreover, it's less conservative than standard tube-based MPC. It has a better performance and it's still efficiently to implement. Thank you for your attention.
Hi everyone, I am Nikos Planagis and I am a PhD student on the National Hi everyone, I am Nikos Planagis and I am a PhD student on the National Technical University of Athens. Our work is entitled Nonlinear Model Predictive Control for the Transient Load Share Management of a Hybrid Diesel-Electric Marine Propulsion Plant. Authors are with the Laboratory of Marine Engineering at the National Technical University of Athens. The problem that is addressed in this work is the performance of the hybrid power plant in extreme transient loading conditions in terms of fueling and emission production. As such, object of this work is the modeling, the design and the experimental implementation of the power smoothing power split strategy for a hybrid marine powertrain. The system that is studied is a parallel hybrid marine power plant. It is a multivariable system with nonlinear behavior. Rotational speed and battery state of charge dynamics are controlled by commands that are provided to the power sources. External mechanical load acts as disturbance. The system is also constrained either by its physical limits or by desired operating limits that have to be taken into account. The modeling was performed based on first principles and measured data. The control system architecture utilizes the measurements and the system model to calculate the optimal ΔU commands that minimize the objective function. The objective function is selected such that a smooth engine transient operation with minimum electric energy consumption is achieved. Input constraints of the system are considered explicitly while output limits are treated as soft constraints. The control system was implemented and experimentally tested at the laboratory's experimental facility. The operating profile during experiments included disturbance step loading. Nonlinear model predictive control operation is compared to the operation of the conventional propulsion plant without hybrid configuration. Controller sampling frequency was selected 10 Hz. From the experimental results, it is seen how the electric motor deals with a fast system dynamics while the engine is controlled to restore the consumed battery energy. Engine performance proves that overshoots are suppressed and engine derives a quasi-steady-like operation with a proposed control strategy, leading to a better overall fuel economy and mean NOx emission reduction. So, thank you for listening and feel free to ask any question if you want to learn more.
Hello and welcome. My name is Lukas Schmidt and I'm a PhD student at the Institute of Automatic Control at RWTH Aachen University. I'm happy to present you our energy management system for hybrid electric vehicles employing MPC. Our main contribution with this work is developing a controller internal model based on experimental data, as well as demonstrating that the nonlinear MPC algorithm is real-time feasible. The control task is to optimally operate a hybrid electric vehicle, meaning that we want to minimize energy consumption while at the same time deliver the requested torque as fast as possible to achieve a good drivability. Because these tasks take place on different timescales, we present a hierarchical framework. The high-level controller, which I will focus on in this talk, addresses the energy efficiency using NMPC for long-term planning and calculating the optimal torque split. The low-level controller employs linear MPC to deliver the driver's requested torque at a fast sampling rate, while at the same time considering constraints and actuator dynamics. For the controller internal model, we first identify in a static modeling approach the actuator efficiencies from steady-state test bench measurements depicted as gray dots. We model a mathematical relation between mechanical power and resulting consumption with second-order polynomials which are twice continuously differentiable and therefore suited for our gradient-based optimization algorithm. Secondly, we model the battery dynamics using an equivalent circuit model. The necessary parameter identification is carried out with simulation experiments with a high-fidelity model of our project partner and least squares methods. Putting it all together, we arrive at a nonlinear program to be solved at every time step. We employ a multiple shooting algorithm for discretization, resulting in both states and inputs being optimization variables. Additionally, we employ soft constraints for state and output constraints to guarantee feasibility of the NLP at all times, which is especially important for real-world applications. Lastly, our chosen integration scheme is a simple Euler backward scheme. We generate code from our NMPC scheme and in addition for our plant model at the low-level controller and run our algorithm on rapid control prototyping hardware. The NLP is solved with a self-written SQP algorithm. Within that, we use the open source frameworks Casadi and QP-Oasis for solving the sub-QPs. From testing, we see that the SQP algorithm needs only 4 SQP steps to converge to our desired accuracy of the KKT conditions. The resulting turnaround times achieved on the embedded hardware are reported in the table and well below the respective sampling times, which renders our approach real-time feasible. Lastly, I want to show the resulting battery state of charge trajectory of our framework compared to the DP solution calculated offline for the VLTC. As a similar trajectory already suggests, the fuel consumption is only 1.8% higher than the globally optimal dynamic programming solution. Thank you for listening. If you want to know more, I'm happy to answer questions.
Good morning, everybody. Good morning, everybody. My name is Paweł Domański, and I would like to present our joint work together with Mr. Wawrinczuk on multi-criteria control performance assessment for multivariate MPC control. We come from Warsaw University of Technology, Warsaw. Our job was motivated by the fact that in the industry we hardly can meet the Gaussian properties, and thereby there is a need to find out nonlinear and non-Gaussian approaches to the task of control performance assessment. The rationale of our job comes from the fact that the real signals from the process industry, they are hardly Gaussian. We can see in the signals the fact that they are non-stationary, they are trended, they have embedded oscillations. We can meet different kinds of outliers that come from the fat tail distributions or external ones generated by erroneous data points. And we can also meet different multiple stochastic generating mechanisms behind it. To measure the poor quality of control, we can use different indexes. Apart from standard mean square error or integral absolute error, together with the standard deviation, we suggest to use robust indicators like, for instance, gamma scaling factor from the alpha stable distribution, robust standard deviation using M estimator with logistic psi function, and different kind of these. In this slide, I would like to present the setup for template for our simulation experiment together with the scenarios that we have considered, and the results can be presented in the tables, which are difficult to be read, or they can be represented in form of the radar plot, which is much easier to be read and to be interpreted. Concluding, first of all, in real processes, we need non-Gaussian approaches. We have tested different CPA measures applied to the MPC tuning. First of all, we have shown that standard measures of mean square error and standard deviation together with rational entropy fail to detect wrong tuning, in contrary to the internal absolute error, robust standard deviation, scaling factor of the alpha stable distribution, and differential entropy. Finally, the task of the assessment for the MPC multivariate control cannot be solved by single index, and thereby we need multi-criteria approaches, and we suggest to use radar plot as the simple representation of the complicated and multi-criteria results. Thank you very much for your attention. In case of any questions, please contact us. We'll be happy to answer. Thank you very much. Bye.
Hello everyone, my name is Matt Ellis. I'm with the Department of Chemical Engineering, where I'm an assistant professor at UC Davis. Today I'll be talking to you about economic MPC applied to systems with dynamics over multiple timescales. More specifically, I'll be considering systems that are written in this standard singularly perturbed nonlinear system form shown here. X is a slow state. Z is our fast state. It's a fast state because we have the multiplication of the time derivative of Z with a small parameter epsilon. Now we assume that the full manipulated input vector can be partitioned into two groups. So we have the slow input, US, which are the inputs that affect the slow subsystem. We have a fast input, UF, which are the inputs that affect the fast subsystem. And as in standard economic MPC form, we assume or design an economic running cost, which we try to minimize over a horizon. And we can also account for system constraints. So to highlight the overall composite multi-rate economic MPC architecture that we design in this work, a block diagram here is shown. It's a composite control structure in that we treat the full system as effectively two subsystems and design a controller for each subsystem. So in this sense, the slow eMPC controls the input to the slow subsystem, and a tracking MPC controls the input to the fast subsystem. It's a multi-rate architecture in that the state vectors are sampled at different rates. So more specifically, the slow state vector X is sampled much slower than the fast state Z. The MPCs themselves are implemented in a standard receding horizon fashion, so that means that they're going to be executed at their corresponding sampling rates. Finally, the overall design approach here that we employ is inspired by multi-rate digital control of nonlinear singularly perturbed systems. One of the key points here is we take advantage of recent advances in the context of economic MPC without terminal constraints, in that we utilize multipliers from the economic steady state optimization problem as terminal penalties. So within this context, we design the eMPC to render the steady state of the slow subsystem exponentially stable, and then we design the tracking MPC with specific stability requirements. I encourage you to check out our paper if you're interested, or come to the...
This talk is titled Lyapunov-Based Economic Model Predictive Control with Taylor Series. This talk is titled Lyapunov-Based Economic Model Predictive Control with Taylor Series State Approximations by Keshav Kasturi-Rangan and Helen Durand. This talk focuses on Economic Model Predictive Control, or EMPC, which is a class of model predictive controller MPC designs. MPC is an optimization-based control formulation that uses a process model for making predictions of the future state to determine optimal control actions at each measurement sampling time. When the objective function of this controller is allowed to take a general scalar form, the resulting MPC is called an EMPC. Important considerations for EMPC are its computation time and also whether it maintains closed-loop stability. For EMPC, closed-loop stability is not necessarily the same as steady-state tracking. For a formulation of EMPC known as Lyapunov-based EMPC, or LEMPC, it is associated with the controller maintaining the closed-loop state in a safe operating region, reflected in the figure as the red region omega rho. The objective function, or economics, is roughly most freely optimized in a subset of the safe operating region, shown as omega rho E in the figure. This subset can be larger when there is less plant model mismatch. Generally, the mismatch is assumed to come primarily from the unmodeled dynamics, though it can also come from numerical error in approximating the solution of the process model used in the controller. Often, it is attempted to make numerical errors small, as reflected in the figure on the right, where different methods of the solution approximation give approximately the same trajectory. Higher accuracy approximations of the solution of a dynamic model can increase computation time for an EMPC. This work therefore seeks to make precise connections between closed-loop stability considerations and model solution approximation in LEMPC. This essentially allows the implications of numerical error to be characterized for the LEMPC design, including how they impact the stability region subset size, and can facilitate understanding of the trade-off between computation time of the controller and potentially economics via the size of the stability region subset. The specific methodology employed in this work is to focus on a class of nonlinear systems with an analytic right-hand side and analytic solutions. Then, a truncated Taylor series approximation of the solution of the dynamic model is used in the controller. The control formulation is analyzed for closed-loop stability considerations, with the truncation error for Taylor series allowing derivation of a relationship between the approximation of the process dynamics and closed-loop stability considerations. For example, the size of a subset of the safe region of operation is explicitly related to the number of terms in the Taylor series approximation. Smaller error resulting from the model solution approximation allows a less conservative subset of the safe operating region to be used in the control law design. Larger error may lead to greater conservatism, but also may decrease computation time. We gratefully acknowledge financial support from the Air Force Office of Scientific Research.
Hi, my name is Wei-Han Chen, a graduate student at Cornell University. Hi, my name is Wei-Han Chen, a graduate student at Cornell University. In this work, we developed a novel data-driven robust MPC framework to achieve efficient irrigation control for stem water potential. Traditional irrigation systems aim to preserve the soil moisture level by efficient configuration of water resource. However, the factor that... Hi, my name is Wei-Han Chen, a graduate student at Cornell University. This is the work I did with my advisor, Professor Fengqi Yu. We proposed a novel data-driven robust MPC framework for automatic control of greenhouse indoor climate. Controlling greenhouse climate is an important issue to protect plants and crops, but disturbances such as ambient temperature and solar radiation would affect greenhouse climate a lot. Although MPC could take weather forecasts into account to minimize the influence, the underlying forecast errors are still the uncertain disturbances that could cause greenhouse climate to become harmful to plants and crops. The essential concept of our work is to combine dynamic models of greenhouse climate with data-driven models that identify uncertainty in weather forecast error. Finding an appropriate uncertainty set for uncertain disturbance is an important factor for robust MPC. If the uncertainty set is chosen too small, protection would be inadequate. On the other hand, if it is chosen too large, the control trajectory would be over-conservative. Therefore, the uncertainty set should be chosen precisely. We adopt a machine learning approach, support vector clustering with weighted generalized intersection kernel to form uncertainty sets of temperature and solar radiation due to its capability of handling asymmetry and correlation in the uncertainty distribution, as well as tackling outliers. SVC approach tries to find the minimal sphere radius that can capture data, and WGIK is implemented when solving the dual form of SVC optimization problem. It is well suited for robust optimization due to its piecewise linearity. A case study of controlling greenhouse temperature for tomatoes in New York City is presented. For comparison, on-off control, certainty, equivalent MPC, and robust MPC are also implemented. The figure here shows that the proposed DDR-MPC framework could prevent the greenhouse climate from violating temperature constraints that would do harm to tomatoes. Although ThA01 uses less energy than DDR-MPC, ThA01 violates the temperature constraint significantly more often than DDR-MPC. Also, DDR-MPC approach ends up with less energy usage than on-off control and RMPC while having nearly no constraint violations. Therefore, the proposed DDR-MPC approach can improve the control performance and reduce energy usage for greenhouse climate control. Thank you for listening. Hi, my name is Wei-Han Chen, a graduate student at Cornell University. In this work, we developed a novel data-driven robust MPC framework to achieve efficient irrigation control for stem water potential. Traditional irrigation systems aim to preserve the soil moisture level by efficient configuration of water resource. However, the factor that really affects plant performance is stem water potential rather than soil moisture level. Therefore, the more direct approach would be sensing the water potential inside the tree trunk or stem. Such measurements are made possible with emerging tools such as a microtensiometer. The dynamics of water flow through soil, roots, and the tree trunk could be modeled by a circuit analog. Soil, roots, and the tree trunk serve as both capacitors and resistors in the system. Evapotranspiration is the driving force of the RC circuit model. Another input is the water inflow, which is contributed by the precipitation and irrigation amount. The dynamics of water potential in the soil, root, and trunk can be represented approximately by the system of nonlinear ODEs. In the water dynamic system, disturbances are evapotranspiration and precipitation. MPC could utilize weather forecasts to help irrigation control. However, the underlying weather forecast errors could cause stem water potential to go below the minimum acceptable value, and plants would suffer from water stress. To deal with the weather forecast error, we adopt a machine learning approach to support vector clustering with weighted generalized intersection kernel to form uncertainty sets of evapotranspiration and precipitation. A case study of controlling stem water potential of an almond tree in California is presented. For comparison, on-off control, certainty equivalent MPC are also implemented. The figure here shows that the proposed DDR-MPC framework could prevent the stem water potential from going below -15 bar, which is a constraint that we set to protect almond tree and crop. This table shows that DDR-MPC uses the least irrigation amount comparing to on-off control and ThA01 with no constraint violation at all. Therefore, instead of controlling the soil moisture level, irrigation control based on the water potential inside a tree became a possible method. And the proposed DDR-MPC approach can improve the control performance comparing to the other control strategies. Thank you for listening.
Hello everyone, welcome to our remote rapid interactive of our paper, which carry the following title, Tube-Based Robust MPC for Distributed Parameter System Modeled as Polytopic LBV. Firstly, my name is Jawad Ismail, and I am a scientific assistant of Professor Liu at the University of Kaiserslautern. This paper introduces a simple online feed-forward and feedback approach for active vibration damping control using a robust tube MPC, which is applied on a nonlinear flexible system for vibrational damping control. This paper discusses also a possibility of embedding nonlinearities inside the linear parameter varying system and thus make use of a numerical low-demanding linear MPC. The resulting mismatches are treated as parametric and additive uncertainties in the context of robust tube MPC. Exact embedding is also possible with existing literature. For the proposed approach, most of the computations are carried out offline. Only a simple convex quadratic program is conducted online. Additionally, a soft constraint extension is proposed. The uncertain system is firstly decomposed into a nominal and error states of the uncertain system denoted as Z and U respectively. Corresponding initial states and constraint from the nominal dynamical system, the robust tube MPC can be proposed. We impose also general hard constraints on the state input space given in polytopic representation. A maximum positive invariant set is computed as a terminal set, and sets are tightened by means of disturbance invariant tube known to be the minimal robust positive invariant set, and for simplicity, a convex hull of the union of each approximation of minimal robust positive invariant set given for vertices of the LPV system are considered here. Additionally, soft inequality constraints are added, which idea is shown in this picture. Together, with the help of the nominal state, the control sequence, a feedback policy is obtained known as the dual mode paradigm. In this example, both open-loop and closed-loop simulations with the objective of active vibrational damping controlled are carried out on the example of a flexible stacker crane. Stacker cranes contains two moving masses and a flexible link, which vibrational behavior must be controlled. This problem is solved in terms of tube-based MPC as online closed-loop control. 35 Monte Carlo simulations has been conducted to demonstrate the robustness. Tube-based MPC is benchmarked with the nonlinear MPC shown in magenta. Results demonstrate the convergence property of tube-based MPC. Thank you for your attention.
Hello everyone, I'm Ibrahim Binu, and today I'll be talking about our work on on-the-fly control of smooth unknown systems. This work is motivated by the problem of trying to land an aircraft and autonomously that has suffered from a catastrophic damage mid-flight. Clearly, this problem requires on-the-fly control of what is now an unknown system using limited data. In this work, we designed a state feedback data-driven controller using optimization. Our method combines smoothness of the unknown system with the data available from a single finite horizon trajectory and can also accommodate side information if it is available. Our approach is computationally efficient since it solves a linear program at each time step. The problem setup goes as follows. We are given data from a single trajectory. We are told what the control constraints are, and the desirable behavior is encoded in known one-step cost function, small c. The dynamics, which is nonlinear, is known to be smooth, but the dynamics as it is not known. At each time step, given the current state xt, we minimize an unknown cost function capital C subject to the control constraints. As you can see here, we focused on a one-step controller because we cannot plan for the future. We do not know what dynamics are. By on-the-fly control, what we mean is that we can evaluate the cost, the unknown cost function and its gradient only for the controller that was selected at that time instant. Our method can accommodate side information on C, including C is monotone, convex, or has known bonds. However, this information is not necessary for the algorithm to work. Our approach, which we call C2opt, utilizes the fact that since C is smooth, it accommodates data-driven over and under approximations. Therefore, at each time instant, it minimizes a linear combination of these approximations. We were able to show that for alpha equal to half, this optimization problem actually is linear, resulting in a computationally efficient solution. We applied C2opt on landing a damaged aircraft, where the damage resulted in unknown nonlinear perturbations to the longitudinal dynamics. We found that C2opt took less than 0.2 seconds at each time step when starting from an initial trajectory that was randomly drawn for 10 time steps. Come see us in our digital poster session where we can discuss this example in more detail and also discuss how C2op beats existing methods. A version of C2op also enjoys sublinear regret as well. Thank you for listening.
Hi there, my name's Huck, and my co-author's name's David. We work at Honda Research Institute, and today I'm going to be talking to you about some work we did last summer to develop an accurate trajectory following algorithm. So, motivating accurate trajectory following, consider you have an automated vehicle. It needs to avoid collisions with moving obstacles and get to a goal. You generate some trajectory, and if you don't follow carefully enough, you might crash. So, now diving into various trajectory following architectures, consider this case. You have a trajectory planner and you just want an open loop controller. So you have steering angle and speed signals sent to this controller, and depending on the current time, the steering angle and speed is interpolated, and you send those signals to the plant. So this can happen very quickly while your planner is updating, but you're not taking into account the current state. So this is a naive approach, but in this work it's incorporated for comparison. And case B is what is actually the state of the art. So you're solving an optimal control problem for your trajectory follower. And this is taking into account the state of the vehicle, and the one thing that it's not doing is it's not passing, if you can see here, the trajectories for steering angle and speed to the trajectory follower. So the control signals are not incorporated into the problem at all. So if the planner is taking a long time to update, then this the control signals that are sent to the plant might become very jittery. There's no reason that they have to be any particular values. They could jump all over the place. So the idea in this work is to pass those control signals to the trajectory follower. And in this paper, we include those trajectories in the cost functional of this optimal control problem. And we compare the three cases that I just discussed in a whole bunch of trials where we vary the obstacle speed and size of an obstacle that's traveling directly towards the vehicle. And you can see that, of course, when and collision is a red dot. So you can see as the obstacle gets bigger and faster, it becomes harder to avoid. Now, you can see that by using this approach, we're improving safety dramatically using the control signals in the cost functional, and we're doing that by improving tracking error and orientation error. And finally, it also improves performance, which is the time to the person. So this is a person following algorithm.
This paper is titled Enhancing Practical Tractability of Lyapunov-Based Economic Model Predictive Control by Helen Durand and Dominic Messina at Wayne State University. The premise of this work is that...
Hello, my name is Charlotte. I'm a graduate student.
This paper is titled Enhancing Practical Tractability of Lyapunov-Based Economic Model Predictive Control by Helen Durand and Dominic Messina at Wayne State University. The premise of this work is that the ability to verify that an automated system will operate a process safely is critical for the application of control to that process. A common control design used in the chemical process industries, where safety is of paramount importance, is Model Predictive Control, or MPC, which is an optimization-based control law with constraints including a process model. The objective function of the controller's optimization problem has traditionally been formulated to track a steady state, but a more general formulation of MPC, meaning one that uses a general objective function and is therefore known as Economic Model Predictive Control, or EMPC, because that objective function can explicitly represent process economics, may not track a steady state. Instead, it might operate a process within a region of state space. Then, safety is considered to mean that the state is maintained in that region of state space. An example of an LAMPC formulation with constraints that allow this safety concept to be guaranteed under certain control theoretic conditions is Lyapunov-based EMPC, or LAMPC. This work explores the concept that perhaps verifying that certain theoretical conditions required for safety under this controller could be made easier in the sense that an end user might expect the conditions required for safety to be more likely to be met for given parameter values used in the control law without explicitly checking, but using a modified implementation strategy. In this implementation strategy, state measurement use in assessing and reacting to safety considerations is decoupled from the sampling frequency of the LAMPC. State measurements are assumed to be available much more frequently than the frequency with which the LAMPC uses them, and are used to check throughout the LAMPC sampling period whether the closed-loop state has left a subset of a set referred to as the stability region, which is an estimate of the region of attraction. When the closed-loop state at any of the times that the measurement is taken is outside of the subset of the stability region, a backup controller begins to be used instead of the LAMPC for the remainder of the LAMPC sampling period. The result of this is that it allows less restrictive conditions to hold on the size of the subset of the stability region than if the LAMPC sampling period was used to design the subset of the stability region. This may increase confidence that closed-loop stability or safety would be maintained under the controller even if the size of the subset of the stability region was not rigorously set using control theory, by effectively making a larger number of sets have the ability to guarantee closed-loop stability such that even potentially ad hoc selection of a set may have a greater likelihood of maintaining the closed-loop state in the desired region. It also opens up the possibility of potentially tuning the size of the subset of the stability region online by modifying it to be smaller whenever the backup controller is implemented in the sampling period after a given size of the stability region subset is used. We gratefully acknowledge the National Science Foundation and Wayne State University for their financial support.
Hello. Hello, my name is Charlotte. I'm a graduate student in the MPC lab at UC Berkeley, and I'm going to be presenting task decomposition for iterative learning MPC. Recently, there's been a big push towards the topic of learning and control. My lab has approached this through Iterative Learning Control, or ILC, in which the controller uses collected data from previous task iterations in order to improve its closed-loop performance at the current iteration. For example, a car that is learning to race around a given track, improving its lap time at each iteration. However, ILCs learn a policy for a specific task environment, so if the environment changes, you have to design a new ILC. And ILCs need to be initialized with a feasible trajectory during the first iteration of a new task, and finding such an initial trajectory can be difficult for complex tasks. Our goal is to use stored state and input trajectories, called executions, that solve n different tasks t and n different environments theta in order to find a feasible trajectory for a new task in a new environment, theta n+1. For example, can we find a feasible trajectory around a new racetrack using stored trajectories from previously raced tracks? We propose task decomposition, a simple but robust approach in which we assume that our control tasks can be decomposed into the same subtasks. Here, tasks are a concatenation of subtasks solved sequentially. For example, two racetracks may look different overall, but be composed of the same straightaways and curves, each representing a subtask. And if a new task is made up of subtasks that were solved previously, though perhaps in a different sequence, then we can piece together stored subtask trajectories in order to design a new task trajectory. The first step is to break the new task into previously solved subtasks. Then we transfer the subtask trajectories to the new task, giving us information about how to solve individual components of the new task. Lastly, we'll try to piece the subtask executions together to form connected trajectories out of these segments. We use a data-driven reachability analysis. First of all, notice that in the last subtask, all of the stored trajectories go to the end of the new task, thereby solving it. Next, we populate the previous subtask with the stored subtask trajectories. And then for each transfer trajectory, we determine if its last state can be controlled to the first state of a trajectory through the next subtask. If yes, then all points in that subtask trajectory are also controllable to the end of the new task. And if not, we remove the subtask trajectory from our task data bank. We again populate the preceding task with stored trajectories and repeat the controllability analysis. As we move through the rest of the new subtask sequence, we form long trajectories out of trajectory segments, verifying controllability only at points of subtask transition. The resulting trajectory is guaranteed to satisfy all state and input constraints in the new environment, incurs no higher closed-loop costs than a trajectory found using a simple initialization method, and can be used to directly solve the task, initialize an ILC, or for approximate dynamic programming. The proofs for these claims and results from autonomous racing and robotic pathfinding applications are found in the paper. Thank you very much for your attention.
All right, thank you so much to all of our presenters. Now is time to move on to the interactive portion of the session. So once you vote for the people's choice, or you can wait to vote until noon, but then go on back to the main program, find their individual links for all the presenters, and you can ask in-depth questions. So thank you so much for all of you for joining, and please move on to the interactive portion of the session. Thank you.